Good evening, everyone. So today we are. Uh, this is the 10th lecture for the problem-solving session for the Introduction to Probability Theory and Statistics. In today's week, we will going to see the problems on the topics covered in this week's class: the point estimate, method of moments, method of maximum likelihood, and interval estimation. And in this I will also talk about the hypothesis testing. It is related to the interval estimation, so we will look to certain questions which are based on hypothesis testing. So before that I will introduce you what is the hypothesis testing is. So we will cover these things in this session. So first I will go through the formulas which were taught in the class. So first was the estimator. So okay, what is happening? Okay, just a minute. Okay. So when we have a population, okay, and we want some information for the population, then it is not possible to go through each person and ask them questions. So other than that, what we will do, we will take some random sample which we talked earlier. We will take some random sample, and based on the statistics of this random sample, we will estimate the parameters for the population. Okay, so we took this random sample and then we will do some statistical analysis for that sample, and based on that those statistics value, we will estimate the parameters for the population. Okay, so here it is the term comes estimator. So estimator is when we estimate something about the population by knowing the information regarding the sample. Okay. So the first point estimators, or we can so to find this we have this methods of estimation. Okay, one is method of movement. Okay, so in this we will equate the movement of the sample with the population. So for example, the expected value of the sample, expected value for the sample X is equal to the mean of population. Okay, this is the one estimation. So can you guys confirm that am I audible? Nitya, am I audible?
Yes, you're audible.
Okay. Okay, and similarly we can equate the second order moment, which will be expectation of x square. So this we can also equate to the second order moment of population. Okay, so this is the first method. Then second method is method of maximum likelihood. So this is an interesting method. In this we will find this value, which is Lx comma theta, where theta is the estimator, unknown estimator. This will be equal to multiplication over all the i's from 1 to n, fx I theta belongs to some big theta. So this f function is for population, belongs to the population. Okay, and in this we will, in this function, in this population function, we will fit this is the sample data. So we will put these sample data values in this function, then multiplies all those values together, and which will give us this L, which is the likelihood function. Okay, so I will explain it with an example. So let's take fx comma lambda is equal to lambda e to the power minus lambda x, exponential distribution. We will find this L function, which will be multiplication of over all the n's, this lambda e to the power minus lambda xi. So this is nothing but lambda to the power n e to the power minus lambda into summation xi from I equal to 1 to n. Okay, where lambda is 0 to infinite. Now we will take log normal on both the sides. This will be e to the power minus lambda. I am just writing summation xi over i's. So this right hand side will become n ln lambda. These are multiplication, so addition ln e to the power minus lambda sigma xi. This becomes n ln lambda minus lambda sigma xi. So as this is e to the power, so we can bring this quantity here, and this will become ln e, which is 1. Okay, So now we will partially differentiate this function with the parameter of the function, which is lambda. So we will differentiate it, this lambda, we will differentiate this quantity with lambda. So this will give us n by lambda minus sigma xi, which will give us lambda is equal to n upon sigma xi, which is 1 upon lambda is equal to sigma xi by n, and this is nothing but expectation of the sample. Okay, so this is equal to 1 by lambda, where lambda is the function of population. This is the parameter for function associated with population, and this is the sample expected value. Okay, now let's suppose we have two parameter function. Suppose this fx is a normally distributed function, root by sigma e to the power minus 1 by 2 okay. Now we will do the same thing. L is equal to L mu sigma will become 1 upon root 2 pi sigma L is okay, so this will become 1 upon root 2 pi sigma to the power n, because we are multiplying this quantity for all x's. So this term will be multiplied for n times, that's why this to the power n multiplied by e to the power minus half upon sigma square into summation of xi's minus mu whole square, where I equal to 1 to n. Okay, so I hope you understand this step. So this L became 1 upon root 2 pi sigma to the power n e to the power minus 1 by 2 sigma square summation over I xi minus mu whole square. Now we will take log normal on the both sides. This will become n ln 1 upon 2 pi sigma minus 1 upon 2 sigma square into summation over I into summation over I xi minus mu whole square. Okay, and we can again write this as n ln 1 upon root 2 pi minus n ln so this I am just detaching these two quantities, or there is no need for that. It's just now this will become n ln 1 minus summation over I xi minus mu whole square. So here we are just manipulating a few things. We are just changing mu to mu square. Okay, so this will become, now this will become n by 2. Okay, because here we took this quantity as 1 upon root 2 pi sigma whole to the power n. I am just doing this thing, 1 upon 2 pi. Okay, I am taking square for this, 2 pi sigma square whole to the power n by 2. Okay, I can write this quantity as this 1 upon 2 pi square n by 2, right? So by doing that, this equation will become 1 n by 2 ln 1 upon 2 pi sigma square minus 1 upon 2 sigma square summation xi minus mu whole square. So now there are two parameters, mu and sigma. So I am now taking this as sigma square, the new parameter is sigma square. Okay, so this sigma square can be denoted by y. This becomes n by 2 ln 1 upon 2 pi y minus 1 upon 2 y summation over i's xi minus mu whole square. So now we will first partially differentiate this L value with respect to mu. Okay, this will give us, this quantity will become 0 and this will become minus 1 by y, minus 1 upon 2y into this 2 will come here, 2 xi minus mu, and this is negative minus 1. This will become xi minus mu upon this summation will be there, summation upon y. Okay, this is by 1. Second is we will differentiate this with respect to y. Okay, so this will become, when we differentiate this with y, this will become n upon 2. This is the constant, or we can we will just manipulate it a little. So before this, we will slightly change the terms. This was n by 2 ln 1 upon 2 pi square minus 1 upon 2 sigma square summation is xi minus mu whole square. Now what we will do, we can just separate these two quantities as well, right? So by doing that, our expression will become easy. This is 2 pi, then we can write it n by 2 ln 1 upon sigma square minus 1 upon 2 sigma square xi minus mu square. So now when we differentiate it, because that differentiation will become difficult, so now when we partially differentiate this L value, with this sigma square, this quantity will become 0. Okay, this quantity will become n by 2 into ln x, differentiation of ln x is 1 by x, so this will become sigma square, and this quantity will become sigma.
Now we have to make it back to sigma square or y. In terms of y, we have to write.
So we can write it in, sorry. I will just write it in the next page. Okay, this is y, this is also y, this is y. Now we will differentiate this with respect to y. This term will become 0, plus this will become n by 2 into y. This will become 1 upon 2 y square, okay, into sigma, this will remain constant, and when we equate this to 0, this will become something like this. This 2 will cut. Oh, am I doing anything wrong? Just just a minute. So if we okay. So here, okay. So this was the first equation. This is the second equation. So here we can do one more thing. This is 1 by y, right? So we can I'm just doing a small manipulation. This is n by 2 ln 1 upon root 2 pi. Oh sorry, this is 2 pi, because we are taking n by 2 here. Now we can change this to this ln y. We just took the power y minus 1, and that minus 1 will come here. So this will become minus n by 2 minus 1 upon 2y sigma xi minus mu whole square. Now if we differentiate this will become minus n by 2 y 1 by y plus 1 upon, this is 2 to the power minus 1 by 2 y square, and that minus 1 will come here, so this will become plus, and then this will become xi minus mu whole square. This is equation 2. This is equation 1. Equating equation 1 n2 to 0, we get summation xi minus mu upon y is equal to 0. This was 1.
Excuse me, in the equation 2, how you get that 1 by 2 y square?
So this is y to the power minus 1. So y to the power minus 1, if you differentiate it, this will become minus 1 y to the power minus 2, right?
Okay. So you're taking that y to the numerator?
Yeah. So differentiation of...
Okay, fine. Okay, you're taking that to the numerator, right?
Yeah.
Okay, fine.
So this will become, this is 0. So this sigma xi minus mu is equal to 0. So this is nothing but sigma xi minus n mu equal to 0, which will give us mu is equal to sigma xi upon n. The sigma is over all i's, I to n. Okay, that's why there here is come n mu, because it is this summation is for n times. That's why we will sum over all the xi's and then minus n into mu. So this mu will be summation over xi's upon n, and by this equation 2, which was minus n upon 2y plus 1 upon 2y square summation xi minus mu whole square is equal to 0. This will become, this 2 will cancel out, this y will cancel out, this will become n is equal to 1 upon y sigma xi minus mu whole square. So from here we get this y is equal to summation xi minus mu whole square divided by n, and this y is nothing but sigma square. Sigma square is summation xi minus mu whole square divided by n. So this is how you use this mean likelihood estimator to estimate these parameters for the population from the samples. Okay, from the sample statistics. So from sample, random sample, we calculated this summation over all these xi's and then dividing by this n, and this is nothing but mu, this is random sample, and this is for the population. And also this sigma xi minus mu, this mu we know, this is the new mu, which we will keep here and divide by n. This will give us the sigma square. This is the variance of population. So from the sample statistics we find the parameters, estimated parameters for the population. Okay. Now point estimations are a little difficult to say that accurately the mean of the population is this, okay, and the variance of the population is this. So rather than just specifying a value, we will define a range in which the mean can come. Okay, like so mean of population will lie will lies in a interval. Okay, interval of values, in a interval. Okay, so both mean and variance will lie in an interval. Okay, so for that we will define a confidence interval. So this is 1 minus alpha into 100%. This is the confidence, alpha is the confidence level. Okay, so with this confidence we can say that the mean of the population will lie in this range. Suppose this confidence interval, this alpha value is 0.05. So this confidence this confidence level, this is confidence level. So this confidence level is 0.05. Then we can say with 95% the population mean will lie in the prescribed range. We can say with the 95% probability the population of mean will lie in the defined range. Okay, and how we calculate this range? This range is found by doing this x bar minus z alpha by 2 into sigma by root n to x bar plus z alpha by 2 sigma upon root n. Here this is the, we talked about this in the earlier classes. This is p z alpha by 2, sorry, z is a normal distribution with with mean 0 and variance 1, and this defines the probability that z is greater than, defines z alpha by 2, the probability that our z is greater than this z alpha by 2 is equal to alpha by 2. Okay, this alpha is this confidence level. So these are the formulas. So what is the formula? Range will be defined x bar minus z alpha by 2 sigma upon root n to x bar plus z alpha by 2 sigma by root n. This is the population, this is the population variance, and this is the range for mean value. Okay, this is for the mean, to calculate the range of mean. Okay, when the variance of population is known to us. Okay, here it is known. If it is unknown, okay, if sigma is unknown, we will use the sample variance S to calculate the range for the mean. So range for mean will now become x bar minus t n minus 1 alpha by 2 s by root n x bar plus t n minus 1 alpha by 2 s by root n. This is the t statistics. Okay, so we have this tables for finding these values given this n minus 1 and alpha by 2. Okay, n minus 1 here is the degree of freedom. So in this earlier, this z was a normally distributed. Here this t is a t distribution, denoting the t distribution. Okay. Now another thing is finding the difference between means of two population. Okay, so this is, if we have this two population with n1 and n2 is n2 having the mean mu2 sigma 2 square, mu1 sigma 1 square. Now we want to find that this x1 is normally distributed with this and x2 is normally distributed with mu2 and sigma 2 square. Now this x1 minus x2 is normally distributed with mu1 minus mu2 sigma 1 square by n1 plus sigma 2 square by n2. So we can say that this x1 minus x2 is normally distributed between this. So the confidence interval will become, for the mean, x1 bar minus x2 bar minus z alpha by 2 upon sigma 1 square by n1 plus sigma 2 square by n2. So I am just writing here minus plus. Okay, so this is from minus to plus. Okay. Or I will write and if sigmas are unknown, we use sample variance. So for this we will find a pooled sample variance which is equal to n1 minus 1 s1 square plus n2 minus 1 s2 square upon n1 plus n2 minus 2. And then we will define the range, which will be x1 minus x bar minus x2 bar minus t alpha by 2. And now this degree of freedom will become n1 plus n2 minus 2 into sp upon 1 upon n1 plus 1 upon n2, and the upper limit will become x1 bar minus x2 bar plus t. This I written this wrong. The first we will write the degree of freedom, then we will write the alpha into n1 plus n2 minus 2 alpha by 2 into sp 1 upon n1 plus 1 upon n2. So when the sigmas, when these variances are unknown, then we will use the t distribution and these sample variance, and when it is known we will use the z distribution and these sigmas. Okay, now if we want to find the range of variance, Then we use F distribution. So this is n1 n minus 1 s1 square divided by chi square n minus 1, not F distribution, chi distribution. Sigma square, this will lie between n minus 1 s1 square chi square 1 minus alpha by 2 into n minus 1. Okay, so we will solve few examples and then you will understand this. So let's move to the first question. So we are given 4 values x1, x2, x3 and x4. Then it be a random sample from an exponentially distributed random variable with parameter lambda. Then the mean level estimator of lambda up to 4 decimal is. Okay, so we know this x1 is 8.2, x2 is 9.1, x3 is 10.6 and x4 is 4.9. So what we will find for exponential distribution, we know that this lambda is equal to 1 upon expectation of samples. Expectation of sample is nothing but x1 plus x2 plus x3 plus x4 by 4, which is nothing but summation of all these quantities, 8.2 plus 9.1 plus 10.6 plus 4.9 divided by 4. This will come out to be 8.2. So lambda will be 1 upon 8.2, that is 0.1219. This is the answer. Okay, so we were given some samples, then we find the expectation of that sample, and from that sample we find the population parameter. This is the parameter for population. Because here it is given that it is a random sample from an exponentially distributed random variable with parameter lambda. So the population has a distribution of exponential distribution. So from these samples we found this parameter lambda. Okay. Okay, so I don't think I used the okay. So I was supposed to use this MLE. So which is that this L is equal to nothing but lambda e to the power minus. So okay, I have shown this proof. So that was okay. So in previously we discussed how we found this. Okay, using this MLE, mean likelihood estimator. Here we suppose that this function is exponentially distributed, then our lambda will become 1 upon expectation of x. This 1 upon lambda is expectation of x, so lambda is 1 upon expectation of x. So this we directly used in this question.
Screen is not visible.
Okay. So previously we discussed how if the population function is exponential distributed, then this lambda value is n upon sigma xi, which is nothing but 1 upon expectation of x. So we directly use that formula in this question, okay, through MLE, and we found this lambda for the population. Moving to the next question. A random sample 100 samples is taken from a distribution with variance 16 for the observed sample mean is 23.5, then the approximate length of 95% confidence interval for the population mean is. So in the question the variance is given 16. This is the variance of population, so this is sigma. Okay, there are total 100 samples, sample size is 100. Okay, sample mean, or we can say the expectation of x or the x bar, sample mean is 23.5.
Please screen not.
Okay, sorry. So this variance, population variance is given 16 sigma square, sample size is 100. In this mean of sample is given 23.5. we need to find range of population mean with 95% confidence interval. So for this we know the formula, the range will be, we don't need to find range, we want to find the length of range. So range is x bar minus z alpha by 2 sigma upon root n to x bar plus z alpha by 2 sigma upon root n. Length of range will be, it's nothing but this higher quantity higher limit minus lower limit, this thing minus this thing. So this is nothing but z alpha by 2 sigma upon root n. Okay, so this is the z table. Okay, and we know that alpha is given 0.05, alpha by 2 will be 0.25. okay, so we need to find the value of 0.025. okay, so this is the 0.025, this is this value, here it is 0.025. so this is corresponding to what z, this is 1.96. okay, this is 1.96. so z alpha by 2 is 1.96. so we will put this value here in this
It's negative or positive? In that table it was shown as negative.
so it is negative, but okay, you will take it negative, but I think we take this as a mode value. Just a minute. So you need to take the mode for this z lambda by 2. We cannot take this negative value, or if you take this as a negative, okay, so this lower limit will become x bar minus 1.96 into some sigma root by n. Higher limit will become x bar minus s bar minus 1 minus 1.96 into the sigma by root n. So you can see that this will become x bar plus something and this will become x bar minus something, and these both will be the same quantities. Okay, you understand my point?
Yeah.
Okay, so length of range will be now 2 into 1.96. Sigma is 4 because sigma square is 16, so sigma is 4, and this n is 100, so root n is 10 divided by 10. This will come out to be 1.568. This is the length of range. Okay, range will be different. Range will be x bar minus z alpha by 2 into sigma by root n, and this is x bar plus z alpha by 2 sigma by root n. So this will come out to be 23.5 minus 1.96 into 4 divided by 10. 23.5 plus 1.96 into 4 divided by 10. This range will come out to be 22.716 to 24.284. Length of range is this higher limit minus lower limit, 24.284 minus 22.716, which is 1.568. Okay. So moving to the next question, question 3. So now a random sample of 16 value is given from a normal distribution with unknown mean and unknown variance. But we observe the sample mean is 16.7 and sample variance is 7.5. So find the rightmost end point of 95% confidence interval of sigma square. We need to find the range for the variance here. So formula for range of variance is x bar minus t n minus 1 alpha by 2 into sample variance to x bar plus t n minus 1 alpha by 2 s upon root n. In the question we are asked about rightmost point of range. The rightmost will be this. Okay, so we need to find x bar plus Tn minus 1 alpha by 2 s upon root n. X bar is given 16.7, s square is given 7.5, and n is 16. Okay, and alpha is 0.05. So first step is we need to find this value. So t 0.025 as alpha is 0.05, comma, degree of freedom is 16 minus 1, 15. So from this t table we can find this value. So so this for t 0.025 and with degree of freedom, here we have given the degree of freedom, so we have 15 degree of freedom. So for this degree of freedom and this alpha 0.025, we get this value of 2.131. Okay, with this 0.025 and the degree of freedom 15. So this value is 2.131. So now this x rightmost value is x bar plus t 0.025 comma 15 into
Not visible.
Sorry, by root n. X bar is 16.7 plus 2.131 into root 7.5. N is 16, so this is 4 root n. So this value will come out to be 18.16. This is the higher quantity, the largest quantity of the range. Okay, the rightmost quantity. Okay, so this was asked in the question. Moving to the next question. So to estimate the portion of voters who plan to vote for candidate A in an election, a random sample of size n from the voters is chosen. Okay, so we have a large population, and from that we want to estimate how many voters are planning to vote for candidate A. So we choose a random sample from the population, and size of that random sample is n. Now the sampling is done with replacement. Okay, now let theta be the portion of voters who plan to vote for candidate A among all the voters. So theta is the portion, okay, who are voting for candidate A. Now how large does n need to be so that we can obtain 90% confidence interval with 3% margin of error? That is how large n need to be, such that probability that x minus 0.03, this theta, which is the proportion of voters, this theta will lie in this range, and probability for theta lying in this range is greater than 0.9. So we need to find the value of n. Okay, so we have a population. We want to find we will need to find the value of n so that the probability this probability should be greater than 0.9. What is theta? Theta is the proportion of voters for candidate A. 0.03 is margin of error. So this is nothing, margin of error is nothing but this z alpha by 2 into sigma by root n. Okay, this is the margin of error. So we need to find this n value, this n value such that this will hold. Okay, so from this equation we came to know that we want this probability to be higher than 90, which means that we want our confidence interval with 90% of confidence. We want our theta should lie in this range. Okay, previously what we are doing, we are finding some range with some confidence interval, with some confidence level. Now in this question we are given this confidence level which is 90%, and here we are given this range also, this margin of error also. Okay, so from this 0.9 we can find this alpha. So alpha is 1 minus this 0.9, which is 0.1. Okay, and so this z alpha by 2 will be nothing but 0.05. So this value is around 1.645 from the z table. Now we need to find this sigma upon root n. How we can find this value? Now for a binomial distribution, Bernoulli, just a minute. Just a minute. So in the question we are given that how many people cast the vote for candidate A. So for the let's suppose that there are only two candidates. Okay, the A and B, and we assume that 50% is casting vote for A and 50% are casting vote for B. It's not like this probability of casting vote for candidate A is 50% and casting vote for any other candidate. Okay, like so we assume that so people either will cast vote for candidate A people will cast vote for candidate A, and they will not cast vote for candidate A. So what we can take this as a Bernoulli distribution. What Bernoulli distribution says that if xi is equal to 0, it has a probability 1 minus p, and if xi is equal to 1, it has a probability p. So here 1 means yes, if a person is voting for candidate A, it is with the probability small p, and if it is not casting the vote, it will be 1 minus p. Alright, we can take this as a Bernoulli distribution function. So for Bernoulli, sigma is p into 1 minus p. So this, now what should be the value of p? So if we take p equals to 1, then this variance will become 0, there will be no variance. Okay, but we know we want to find it for the maximum variance. Okay, so if this sigma will become 0, then there is no sense of calculating this n value, because this margin of error is z alpha by 2 into sigma. If this will become 0, then we cannot find this n value, and we need to find the maximum n value, maximum value of n. So for that we want this sigma to be maximum. Okay, so if we want this sigma to be maximum, we can do one thing, we can differentiate this sigma with respect to p and equate it to 0. So this will become nothing but this is p minus p square. This will become 1 minus 2p. So p, from here p came out to be 1 by 2. So this sigma will come out to be 1 by 2 into 1 by 2, which is equal to 1 by 4. So now we are given this margin of error is 0.03. This is nothing but z alpha by 2 into sigma divided by root n. Z alpha by 2 we calculated, this is 1.645. Sigma we calculated, it is 1 by 4. 1 by 4. Achha, okay, this is sigma square. Sorry, this is sigma square. And here we need to put sigma value. So this will be 2. Sigma square is 1 by 4. Sigma is 1 by 2. So we were putting 2, and we know this n is, we need to find this value n. This is equal to 0.03. So from here we will find this n is around 752. So sample size should be around above 752 if we want that this margin of level should be 0.03 with confidence level 90%. For that, this value of n should be greater than 752. Okay, this should be greater than 752. So from here this value comes out to be 752 around, and if we want that our margin of error is 0.03 with the confidence level 90%, then our n should be around 752 or above 752, not less than 752. So in this question we had applied this concept of Bernoulli, so which is very good. So that's why it is a very important Very important example. Okay. Moving to the next question. So we are given a sample of 144 elements is given from a distribution with unknown variance. For the observed sample, the sample mean is 55.2 and the sample variance is 34.5. Now we need to find the interval for mean of the population. Okay. So we are given this sample mean which is 55.2, S which is 34.5. This is sample mean, sample variance. This is sample variance and alpha is given to be 0.1. 0.01. It's 99%. So alpha is 0.1. So we need to find the range for mu. When sigma square is unknown. So when sigma square is unknown, we will use this t distribution. So range will be x bar minus t alpha by 2 n minus 1 into s by root n, x bar plus t alpha by 2 n minus 1 s by root n. So when you find this value, this will come out to be, so this t alpha by 2 n minus 1, you will find this value is around 2.58 and this range will have come out to be 53.94 to 56.46. So we will just check these values. So alpha is 0.01 and n is 144. So we need to find this for degree of freedom will be alpha by 2 is 0.05. This will be 143. So this t value for 140
it's 0.01 or 0.05.
It's 0.05. It's 0.005, sorry.
Okay.
It's 0.005. Because it is alpha by 2, right?
Okay.
So I am right now. We are using now. So from this table we can see for t.05. Okay, so we don't have this 0.05. There is t.05. For this n is 144. So we have this for 100. For 100 it is 1.66. For 40 it is around 1.684 and for 3 it is around it is around 2.132, sorry 2.353. Okay, so just wait a minute. So just so in this we are not given this 143, but you can use some other t table. This is not a very good t table, I just checked online also, or you can calculate it using this table only. I am just checking. There is some formula that is used for calculating this for 143. So so we know this t is 0. So we know this for 40.05 and degree of freedom 100. This value is 1.66. 40.00 sorry 40.05 and 40, this value is
Alpha by 2 or
alpha by 2.
so it's 0.005, right?
No, it is, sorry, it is 95%, right. So these values will be changed. For 100 this is 2.626. For 40 it is 2.704. For 3 it is 5.841. So or we do not want to this. Okay, so we know this y minus y1 is equal to y2 minus y1 upon x2 minus x1 into x minus x1. So we know this equation, right? So here we can take this y2 as 2.626, y1 as this 2.704, x2 as 100, x1 as 40, right? And x is 143, and we need to find this y, and we are given all these values. So we are just interpolating for this degree of freedom 143. We know these values for 140, we want it for 143. So we are using this regression line to predict this. So here these are y2 and y1. We are using this 140 as x1 x2, y1 y2 are these values, and for x equal to 143 we are finding this t value. So this will be nothing but 1 minus y1 is 2.704, y2 is 2.62 minus 2.704 divided by 100 minus 40, x is 143 minus 40. So this is 2 minus 2.704 is equal to this quantity will become 2.62 minus 2.704 minus 0.084 divided by 60 into 143 minus 40. So 0.084 this will become minus 0.1442. So y will become 2.704 minus 0.1442, which is nothing but 2.56. Okay, so this t.005 for 143 is 2.56. So I hope you understand how I find this for degree of freedom 143.
Yeah.
Okay, using this formula.
Cannot take it from the table, the value corresponding to 3?
No, like we need to find it 143. Okay, so it is not like we can add up like 40, 100 plus 40 plus 3. We cannot do like that.
Okay.
Because so we have a regression line here. So by using this we can interpolate for this 143.
Okay.
So now we will put into this value. So by here so this is came out to be 2.56. So here it will be 2.56, and when you put these values here, so we know all the other parameters. So this x bar is 55.2, s is root over 34.5, and this n is 144, so root n will be 12. Okay, so range will be x bar minus t 0.005143 into s by root n to x bar plus 2.005143 s by root n. X bar is 34.
55.2. Yeah.
55.2. This is 2.56. This will be root over 34.5 divided by 12. 55.2 into 2.5, sorry, addition into 34.5 divided by 12. So this range will come out to be 53.94 to 56.46. Or you can just check this values, okay, because in the earlier I have taken this as 2.58. At that time my value came out to be 2.58. At this time it came out to be 2.56. So you can check, these can be slightly different. Okay, but you know how now to find this t value for some other parameter, for some other degree of freedom value. Okay, so by interpolating using it a linear regression. Okay, so moving to the next question now. So we have a random sample from x1 to x16, and it is given from a normal distribution with unknown mean and unknown variance. From the observed sample, we found that the sample mean is 16.7 and sample variance is 7.5. Now we need to find the confidence interval for the mean as well as for the variance with the 95% confidence. Okay, so here we are given n is equal to 16, x bar is 16.
Screen not visible.
Yeah, x bar is 16.7, standard deviation is 7.5, sample variance is 7.5, alpha is 0.05. So first part is we need to find the range of mean. So this will be x bar minus t alpha by 2, n is 16, n minus 1 into s by root n. Okay, 2x bar plus t alpha by 2 n minus 1 s by root n. X bar is 16.7. This value will come out to be 2.13. This is 0.025 comma 15. This is 2.13. From the table you can easily find this. This s will be root over 7.5, n will be 4 comma 16.7 plus this thing. So this values come out to be 15.24 comma 18.16. This is the range for mean. Now we need to find the range for variance. So for the variance, The formula is n minus 1 s upon chi square alpha by 2n minus 1 to n minus 1 s square chi square one minus alpha by 2 into n minus 1. This is the range. Okay, here this chi square values are different. There it is for alpha by 2 comma n minus 1, and here it is 1 minus alpha by 2 comma n minus 1. This is for chi square 0.025. So I don't have the chi square table right now. I just check online. So here this is the chi squared table. So the alpha is, first we want alpha for 0.025. So here this is 0.025 and degree of freedom is 15. So corresponding value is 27.488. Okay, this is 0.025 and this is 15. This is 27.488. So this value is 27.488. Okay, similarly chi square value for 1 minus alpha by 2 into n minus 1, which is chi square for this is 0.975 comma 15. So for chi square 1 minus alpha by 2 into n comma n minus 1, so we need to find chi square for 0.975 with degree of freedom 15. Just a minute. So for this 0.975 and corresponding 15, the value is 6.262. Okay, so this is 6.262. So now we just need to put it into this formula. So range of variance will be 15 into s square, which s square is 7.5, divided by 27.488, because this value 27.488, and 15 into 7.5 divided by 6.262. So this will come out to be 4.09 to 17.97. Okay. Now moving to the next question. Okay, so now I am just going to give a brief introduction about the hypothesis testing. Okay, in this lecture, so we haven't covered, professor hasn't covered it in this session, but
Questions are asked based on that.
sorry.
Questions are asked based on the hypothesis.
Yeah. So that's why I will just give a brief introduction about it, so you will be able to do few questions.
Okay.
Okay. So in this we have a null hypothesis and a alternative hypothesis. This is H0 and we denote it as H1. So null hypothesis is denoted as H0. So what this hypothesis means? Hypothesis means that we have some idea, we have some picture in our mind. So null hypothesis means that if for a given population we just assume or we think that the mean of the population is some mu. Okay, so that will be the null hypothesis, that we assume that mean is mu. Alternative hypothesis will be mean is not mu. Okay, now when we say that this is H0 and this is H1, now we need to verify which of this hypothesis is correct, which of these following thinking is correct. Is mean is equal to mu or it is not equal to mu? So for that we will use the test statistics we used in the previous examples, where we are using this finding the range or confidence interval of these mean and variances. So we will use that concept only here. So now we have some test statistics. So the test statistics are nothing but the values we saw earlier, that sigma by root n, this t alpha by 2n minus 1, s by root n, all these values are test statistics. Okay, so there is one thing, test statistics. Another thing is critical region. So we will find this test statistics and we will find some values based on that. But when to accept this H0 is right and when to accept this H1 is right, for that we will find some critical region, and if these test statistics values lies in these critical regions, then we say that our null hypothesis was correct. But if it is outside this region, if these test statistics lies outside this region, then we will reject our null hypothesis and we say that this alternative hypothesis is correct. Okay, so this critical region is also called this rejection region. Okay, sorry, I said it incorrect. So this is the region, is the set of values of the test statistics for which null hypothesis is to be rejected. Okay, so previously what we are doing, that let's suppose we have some values. we are finding the lower limit and upper limit, and we are saying that our mean will lie in this region. This value is nothing but x bar minus z, let's suppose z alpha by 2 upon sigma root n. This is x bar plus z alpha by 2 sigma upon root n. So we were saying that our mean is in between these values. Okay, now in hypothesis we are saying if our test hypothesis, if our test statistics this and is less than, if we will find this test statistics, and if it is less than some value or is greater than this, if they lies in these region, okay, if they lies in these region, then we will reject the null hypothesis, which is saying that our mean will lie here. So if h naught is correct, okay, if h naught is correct, then mu will lie in this range, this x bar minus z alpha by 2 sigma upon root n, comma x bar plus z alpha by 2 sigma by root n. It will lie in this range. But if it is not correct, if h naught is not correct, then this mu value will not lie in this range. Okay, so now how we will test these hypotheses. Then there are some other things also, like there is one scenario. So let's suppose we rejected null hypothesis when it was true. Okay, there are few cases in which we will reject our hypothesis, our null hypothesis, when it was true. It was true, but we accidentally rejected this null hypothesis, and we concluded that this mean is not equal to some values given from the sample. Okay, that is known as type 1 error. Okay, and it is also called level of significance of test. So this hypothesis testing is a test where we are testing whether what we believed, that this population mean will be equal to some value, is it true or not. If suppose that was true and we concluded from our test that it is not true, then it is known as type 1 error, and it is show the level of significance of our test, that how right accurate values our test is giving. Okay, so we want to minimize this type 1 error. Okay, because we do not want to reject null hypothesis when it is true, so we want to minimize this type 1 error. And there is another error, which is type 2 error, which is failing to reject null hypothesis when it is false, when it is actually false. Okay, so the probability that type 2 error, let's suppose this is beta, it is denoted by beta, it is not supposed like this, I will write it on the probability of type 1 error is nothing but alpha, which we are using earlier, which is the confidence level, and probability of type 2 error is denoted by beta. So then another thing is power of test, which is equal to 1 minus beta. Okay, so we want to minimize this type 1 error as well as this type 2 error. Okay, So these are other things. Now I will just make a table that you can make in your notebook and use it for the questions. Hypothesis testing. When we take our null hypothesis as that mu is equal to mu naught, that our population mean is equal to some value, we are saying, okay, and where sigma square is unknown, we do not know the variance of the sample, variance of the population. In that case, if h1 is mu naught equals to mu naught, then we will reject our h naught when we will find the value t naught if it is less than minus t alpha by 2 comma n minus 1, or it is t naught is greater than t alpha by 2 comma n minus 1. Okay, and this t naught will be this t naught will be x bar minus mu naught upon s by root n. Okay, so if this value is less than this value or it is greater than this is minus and this is plus, then we will reject our null hypothesis. Okay, and if this for the same, that when the h naught is mu equals to mu naught and sigma square is known, then h1 is mu naught equals to mu naught, then we will find this z naught, which will be x bar minus mu naught upon sigma by root n, and we will reject null hypothesis if this z naught value is greater than z alpha by 2. Alpha by 2, we can easily find this value z alpha by 2, and if this z naught is greater than z alpha by 2, then we reject the null hypothesis. Okay, z naught is calculated from this formula. And if we want to find the difference between mean of two population, this is population 2, mu1 mu2 are the means. So if we want to find this, we are saying in null hypothesis that this mu1 minus mu2 is equal to some delta value, or it can be 0. Okay, so this delta can be some value, and this h1 will show that this is not equal to this delta value. So then this test hypothesis, this test statistics will be, first we will find this sp square, which is nothing but n1 minus 1 s1 square plus n2 minus 1 s2 square upon n1 plus n2 minus 2. Then this is, first we will find this sp, and here this variance are unknown. then we will find the degree of freedom, which is nothing but sp square that we find earlier, sp square divided by n1, sorry, not sp, s1 square divided by n1 plus s2 square divided by n2 whole square divided by s1 square by n1 whole square divided by n1 minus 1 plus s2 square by n2 whole square divided by n2 minus 1. This is the degree of freedom. Okay. Then our test statistics will become, this t naught will become x bar, x1 bar minus x2 bar minus minus delta divided by sp 1 upon n1 plus 1 upon n2. Okay, now if this t naught is less than minus t alpha by 2 comma d comma comma n1 plus n2 minus 2, or this t naught is greater than t alpha by 2 comma n1 plus n2 minus 2, then we will reject our null hypothesis. Okay, and if variance are known, then we will find this z naught value, which is nothing but which is nothing but x1 bar minus x2 bar divided by sigma 1 square upon n1 plus sigma 2 square upon n2. And if this is less than minus z alpha by 2 or greater than z alpha by 2, reject null hypothesis. Okay, so there are few of these formulas which can be used. So I'm just I will show the few examples so you can see how to solve the questions. So let x1 to x4 be random sample for a normal distribution. Here mu is unknown. Suppose that we have the following observation, that 4 values are 2.82, 2.71, 3.22, 2.67. Now we would like to decide between these hypotheses. The hypothesis 0 is mu equal to mu naught is equal to 2, and h1 is that mu is not equal to 2. We will assume that this alpha is 0.1. Now which hypothesis will we accept? Okay, so for this we will find first the x bar, which is 2.82 plus 2.71 plus 3.22 plus 2.67 divided by 4. This will come out to be 2.85. And mu naught is equal to 2. Okay, in the question we are claiming that this mu naught is equal to 2, that mu is equal to mu naught is equal to 2. The expected value for the sample is given 2.85. okay, sigma is given 0.01, sorry, alpha is given 0.1. okay, and n is equal to 4. So we will find this z0 value, which will be x bar minus mu naught upon sigma by root n. Because in this question we are given that these are the sample from a normal distribution where mu is unknown but this variance is 1. okay, so that's why here we are using this x bar minus mu naught upon sigma by root n. X bar is 2.85, mu naught is 2, sigma is 1, and it divided by 2. This value come out to be 1.7. okay, now we know so we are saying that if this value, if this z0, we find this z0, if it is greater than z alpha by 2, then we will reject our null hypothesis. okay, so z0 is 1.7. This z alpha by 2, which is z.05, it is equal to 0.1645. so this z0 is greater than z alpha by 2, so we reject null hypothesis. What was the null hypothesis? That mu is equals to mu naught equal to 2. okay, so this is wrong. okay, we reject because this z0 value is greater than z alpha by 2. Similarly, this is the next question. So here we have a farmer weighs 10 randomly chosen watermelons from his farm and he obtains the following values. We are given the following values. Assuming the weight is normally distributed with mean, mu and sigma square, variance sigma square, we need to find the confidence interval for mu. So this is, here we are not using this hypothesis. So this can be done easily using the previous examples. So I will just write the answer for this. For 9th question, the answer is, it will be the mean, this x bar will come out to be 9.259, sample variance, standard deviation will come out to be 3.99. 25,9 is equal to 2.262. So the range will come out to be 6.
It's not visible.
So this x bar from the values given came out to be 9.259. Sample standard deviation came out to be 3.99. This t 0.025,9 is 2.62. So the range will come out to be 6.405 to 12.113. okay, you can check this by doing yourself, and if you have any doubt you can ask in the next session. okay, so that's all for today. okay, so I'm leaving the session now, ending the session now. Okay.
Thank you.
Thank you.